EnterpriseNG. Welcome. I'm Alex Rickabaugh from the Angular team, and today I'm really excited to talk about scalable development of components. If you haven't seen one of my talks before, I'm a software engineer at Google, and I've been working on the Angular team for over 6 years now, since back in the early days of version 2. It's pretty amazing to me that we're on version 13 already. I've worked on a few things on the framework during my time on Angular, including HTTP client and our service worker, but my primary focus for the last couple of years has been the Angular compiler. To start off, I want to define what I mean by scalable components, because there's all different kinds of scalability. It tends to be an overused word. This is a talk about building large, complex components. Components that visualize complex data sets, orchestrate large workflows, render things like dynamic forms, highly configurable components with lots of features. The kind of components that are used by multiple consumers across different applications. And one of the biggest challenges with building these kinds of components is that adding features comes with a cost. It requires adding more code. How do you scale component development and add features that some customers might need without impacting the code size and loading performance of everyone across the board? So really, this is a talk about tree shaking and how to design components and component libraries with tree shaking in mind. We'll start out with a discussion of what tree shaking is and how it works, and then we'll look at what kind of components can benefit from some attention to this optimization. And finally, we'll look at techniques and patterns for designing with tree shaking in mind. So let's start with a short discussion of tree shaking as an optimization. I've heard a number of different explanations and definitions of tree shaking, but this is the one I think is most useful. It's the process that a code optimizer uses to remove any code that it can prove is not actually used at runtime. So here's an example. We have some utility functions for fetching data, getUser and getAccount. They each return different data from different HTTP endpoints. And now we have an app component that calls getUser, but doesn't call getAccount. And so what the tree shaker does is it looks at this code and starts with the application component that's calling our function, getUser. It's able to follow that call to an import statement and finally to the function definition. So in the end, it knows that getUser is a symbol that's referenced from the application component, and getAccount is a function that's not referenced at all. So once the optimizer determines that getAccount isn't actually used, it can remove the code for that function from the final bundle without consequence. And note that this is a transitive and repetitive operation, because removing getAccount might remove the last remaining references to other functions or variables or classes or something, and those can be tree shaken and so on. Or maybe not. So in this example, we've extracted a getURL helper function. And even though getAccount is removed, getURL is not, because it's still referenced by getUser. Now here's a different structure that's doing the same thing. We have a typical Angular service. It injects HTTP client, and it provides two methods, getUser and getAccount. We can inject this into our application component and use it to get the user data that we need. Right? So how is this different? Well, it turns out that this approach is objectively worse when it comes to tree shaking. Remember that tree shaking only works if our optimizer can prove that code is unused. And it's good at proving that functions or classes are not used, but it actually can't prove that a method is not called. So if data service is used at all, the code for both getUser and getAccount will need to be kept. So if we understand how this optimization works, we can choose designs that will optimize well. In other words, where it matters, we can design our code to tree shake effectively. You've probably heard a lot in the last couple years about Angular's Ivy rendering engine. This was one of the foundational principles behind it. Before Ivy, the template of a component was compiled into this thing that we call an ng-factory. And that ng-factory itself referenced an object from Angular core called services. And this object had methods for rendering templates, doing change detection, running queries, etc. Because it used methods on a single object, the entire Angular runtime was actually incompatible with tree shaking as a whole. In Ivy, we made two big changes to rectify this situation. One, removed the generated code from a template into the component class itself. And that way, if nothing references a component, then nothing can possibly reference its template, and the template can be tree shaken away. And secondly, we split the runtime up from a single object with lots of methods into a number of individual functions. And that way, if nothing in an application uses a particular feature of the runtime, a feature of Angular, that part can be optimized away as well. This concern over optimizability goes beyond just removing code that's not used at all. It turns out a similar process also influences how well bundlers like Webpack can split code into multiple chunks when it comes to lazy loading. There's one significant distinction here. Currently, Webpack, which is the bundler used by Angular CLI, only code splits at the level of ES modules. That is, it can only split out code that's declared in separate files. It can't take two functions in the same file and put them in different lazy loaded chunks. And for applications, this is a pretty reasonable restriction. Applications tend to be made up of lots of different files. But Angular libraries are actually flattened when they're published to NPM. So if a library is concerned about code splitting, it has to be divided up into multiple entry points, right? Those are the paths that users import from to get code from the library. Each entry point is flattened into a single file when libraries are published. And this is why the Angular material library is shaped like it is. If you look at the structure of material, each component or logical group of components, along with the associated services and ng modules, etc., is imported through its own entry point. As a result, if an application uses one of these entry points only in a lazy loaded context, that component can be code split away and loaded lazily along with that route. So just like we can design for tree shaking, we can design for lazy loading by splitting out code that's likely to be used independently into a separate entry point. And this isn't free, right? Entry points have both overhead in terms of the bundling process, as well as complexity for consumers. They have to import things from a different path. But it's worth thinking about this as you structure your libraries. So when do these considerations actually matter? When is this important? Unfortunately, I can't give you any hard or fast rules, really. It depends on what you're building, who you're building it for, and what the constraints and the requirements are. For line of business applications that always load over a fast corporate network, these things probably aren't worth spending a lot of time on. But if you're serving a large application in an environment where bundle size is important, for example, if you care a lot about core web vitals, it might be worth spending some time thinking about how your code is going to interact with an optimizer. Or if you're using a library that someone else built in such an environment, you can look for certain signs that it's going to optimize well or not optimize well. Ultimately, my goal is to show you how to approach component and library design with tree shaking as a consideration. Whether that trade-off is worth it depends on the circumstances. A basic example of a component where these kinds of things might be worth considering is a complex data table, something that needs a large feature set to support different consumers with different requirements, where each individual consumer may not use all of the given features. So we've covered what these optimizations are and why it might be useful to consider them when designing. Now let's look at some ideas and some techniques for actually doing that. We're going to cover 3 of them today: using tree shakeable services, moving optional functionality into optional services, and composing components out of multiple directives. Tree shakeable services. This topic can pretty much be summed up as don't provide your services with ng modules, right? And why not? Well, providing a service in an ng module actually creates a direct reference to that service. And the tree shaker is going to see that reference and realize, it can never remove the service, even if nothing is actually injecting it. This is complicated by the fact that users tend to import and reference these ng modules in more places than is really strictly necessary. For example, if they're using like a shared module pattern. And note here that I'm talking about true services, not things like application configuration that does make sense to include in providers. So here's how we do this. Instead of putting a service in a provider in an ng module, we instead annotate it with injectable and add the provided in root flag. When you add this flag to a service, it makes that service available to be injected anywhere in the application. No ng module necessary. The main benefit of doing it this way is that it doesn't actually add a reference to the service from the application or anywhere else. It can still be tree shaken away if nothing injects it. It can also be lazy loaded if needed, even though it's technically a part of the root injector. The beauty of provided in root and tree shakeable services in general is that we're moving the dependency on the code or service or behavior in question to the consumer. It's the consumer's responsibility to depend on the service. It's not something we do for them. So instead of proactively adding a provider, right, now there's no dependency until the consumer requests the service is injected. And it's this basic idea that actually underpins all of these techniques. So let's look at optional behavior in components. Let's say we're building a date picker. Most customers of Date Picker want to use the modern Gregorian calendar, right? It's probably not even something you think about when you select a date picker. But suppose a few of our customers want to use our date picker for historical dates. And so they file a feature request for us to support the Julian calendar as well. So we can do this. We can add an input and let the user say which calendar implementation they want, right? Check, done. In code, that would look something like this. We have our input. It defaults to the Gregorian calendar because we don't want to make everyone who uses our date picker specify that. But if the user selects the Julian calendar, in ng on init, we choose the right date service implementation to use. Do you see the problem here? The tree shaker actually doesn't know what the value of calendar will be at runtime. It has to assume that both branches of this ng-if could potentially be true, and both calendar implementations are now dependencies of this component, regardless of which one is actually going to be selected, even if, in 99% of cases, nobody uses the Julian calendar. So let's fix this with an optional service. So here, we set up a tree shakeable date service interface. We're being a little tricky. We're using useClass to set a default implementation to the Gregorian calendar. So far, so good. In the component, all we have to do is inject this service. By default, we'll get the Gregorian calendar implementation, and most of our users are happy. Those users that want to pick historical dates using the Julian calendar just have to override the default provider. And they can either do this in individual components, if it's just a couple of them, or they can do that for the entire application, if that makes more sense. And that approach works, but it does tend to be a bit verbose, right? We're forcing our user to kind of care about this provider that they have to set up. It was really nice for them to be able to say calendar equals Julian right in their template. And we can get that developer experience back by using a directive. That would look something like this. Our directive here has a selector that matches against the fancy date picker element, right? So it's only going to match on instances of our date picker component. But it's more specific than that. It's only going to match if they have a calendar attribute that's set to Julian. So this directive binds the alternate date service so that it will be injected instead of the default. And that's really nice, right? Because consumers don't have to be aware that this directive even exists. As far as they're concerned, they're setting a property of the date picker component. And the directive behind the scenes configures the service to work correctly. And this idea of using directives behind the scenes to compose behavior is the last technique that I want to cover. The idea here is that if our component has multiple features, some of which are not always used by every consumer, then we can split those features out into optional directives with selectors that match on properties or inputs of the main component. We can then communicate between the component and these various feature directives to actually implement our features. So let's look at an example of this using the hypothetical data table from earlier. Say we want our data table to support sorting. Not all consumers of the table will need to sort their data, and we don't want them to pay the cost of supporting sorting in the code if they're not actually going to do it. So this is the developer experience we want: a data table component with sort column and sort order inputs. So obviously, we'll start out with our data table component. We're also going to have a directive for the sorting feature that's going to match if either of these sorting inputs are provided. And note that those inputs are on the directive, not the main table. Our table component will have no code related to actually sorting the data. That way, if these inputs are unused, the directive that implements it is not referenced and is tree shaken away. There's two ways we can implement this: push and pull approaches. In the push approach, directives inject the component and push data and configuration to it. In a pull-based approach, components inject the directive and interact with it as a service. I'm going to show you both of these, starting with the push-based approach. To set this one up, our table component needs to expose an API for the directive to talk to. Here, we add a callback function for sorting. There's no code related to sorting. The default implementation of the sort function is just the identity operation. It also has an update operation, which is going to re-render the table. In the directive then, we can inject the table and set up how sorting works in ng-on-changes. Whenever either of our sorting inputs change, we adjust the sort function that the table is going to use using whatever complicated logic we want, and then we tell the table to re-render. In the pull approach, we're going to optionally inject the directive from within the component. This is a little more tricky to set up, but I find that this pattern is actually cleaner and leads to more testable designs. So in our directive, we're going to add a sort API that the table will be able to call. It's kind of the opposite of the other pattern. In the table then, we're going to optionally inject the directive. If the consumer has enabled sorting, right, if they bound any of the sorting inputs, then the directive will be present and we'll be able to inject it. Otherwise, since we're using optional injection, we'll get null. And now when we render the table, we can treat the directive almost as like a sorting service and call it sort API if it happens to be there. There's a little flaw in this example right now. Just attempting to inject the directive actually creates a reference to the directive. And we don't want to do that because we want our directive to tree shake away if it's not used. So we need to break this reference and inject the directive kind of indirectly. And we can do this by using an injection token. Here's what this looks like on the directive side. We create our injection token. We have the directive provide itself. We use a forward ref to get around the fact that we're technically referencing the directive before it's declared. And then in the component, we can inject the injection token. And if our directive is not present, it won't have provided itself and it'll be tree shaken away. These are some very powerful techniques for composing and building scalable UIs. They are not without their drawbacks, right? They can increase the code complexity kind of significantly. Interacting with change detection can also be particularly tricky. Sometimes you'll need to manually delay work using a promise or a set timeout, or manually call the change detector ref. So that's all I have to show you. I know it was a lot of information and some fairly complex examples. I'll tweet out link to the slides and a stack blitz with some of these things actually implemented. My hope here was not to teach you these techniques in depth, but just to give you an overview of what's possible and why it's worth thinking about. So the next time you're adding a new feature to an already complex component, you can decide for yourself whether it's worth taking code size and optimizability into consideration in your design. Thank you very much. Have a great day.
Hi, I'm Joe Weems. Thanks for checking out this video from EnterpriseNG 2021. Online conferences were great, but it's time to get back in person. See your old friends, make some new ones, and take your career to the next level. head over to ng-conf.org to get your ticket. See you there.